Alright team, welcome to another video here. This time we're going to tackle this shear stress topic slightly differently. Now if we have a little look at the component we've got in this question, up in the top corner there, you can see it's a slightly different arrangement than we've had before. Now just to give you a bit of an example of what this thing might look like. So obviously we've got a kind of basic setup here. We've got a trailer that as we drive off, force will pull it in that way, and obviously we've got a force acting here as well. Alright, so if you have a look at the arrangement of that, it's got a little pin there that holds the trailer onto the back of the little four-wheel drive grass cutter thing. So what that causes here, it causes shear stress in these areas. Alright, so it's a bit of an example of what this thing might look like in real life. Now let me just grab that and I'll pop that up there. No, we need it. Okay, so the scenario here, we've got a 16mm diameter pin up here, 60mm diameter. It's part of a mechanical setup, as we've seen in the little video. Sorry, a little image. Shear stress of the pin is 320 megapascals. Ultimate tensile stress is 280 megapascals. Calculate the shear stress. Now, different scenario here. We've got this connection. So part number 1 and part number 2. Part number 2 is going to go in that direction. Part number 1 is going to go in that direction. Now, but because this is a different arrangement than what we've looked at earlier, we've got two areas under shear here. So that's classed as double shear. Alright, double shear. Okay, which means that we're going to have to tackle this question in a slightly different format. Okay, now again, previous videos we'll get stress equals force over area. So force, we've got 5 times 10 to the 3 newtons. Okay, and then we've got area. It's a diameter, so the area is going to be pi times half the diameter, radius. So 8 times 10 to the minus 3 squared. Now I'm going to give you guys a sec to pop that in your calculator, and we're going to get an answer. Now the answer that we're going to get is 24.8. We'll call it 87 times 10 to the 6 pascals. Okay, now although we've got this answer here, this isn't the answer to the question, because as we can see we've got double shear. So what we need to do is multiply that by 2 to give us double that stress. And there's a couple of different ways you can tackle this, but as you pop this in, we'll have a little chat about what that might look like. So on there, we multiply that by 2, so we get an answer of 49.75 times 10 to the 6 pascals. Okay, now that is the answer to this question. That's how much stress is in this bolt, this pin, should I say. It's double. Now, because it's the connection we've got, it's on the top and the bottom, that's why we're having to double that stress value. Now, there's a few different ways you can actually tackle this question. I've done my bog standard force over area and then multiplied that by 2 to give me a double shear. However, what we could do, if we multiply the top calculation by 2, or top force by 2, we'll end up going straight to that answer, or if we multiply our area by 2, we'll end up getting straight to that answer. And you can try a couple of different ways if that's how you want to tackle it. So that's a slightly different scenario than what we've already looked at, and so we'll class in that as double shear. So I've used my single shear calculation, multiplied by 2, and I've got double. Now I'm just going to go back up to this question a sec. We've got a shear stress of the pin is 320 megapascals, tensile 280 megapascals. Now something that we've mentioned in previous sessions is we have this thing called factor of safety. Factor of safety. Okay, and what that does is it takes the ultimate stress that the material can withstand and divides it by its working stress to give us a ratio. So if we use the shear stress of the pin, so we've got 320 times 10 to the 6 and divide that by 49.75 times 10 to the 6, we'll get a factor of safety. Now, no units in factor of safety, so these cancel each other out. So we'd have 320 divided by 49.75, and I'll give you a sec to pop that in your calculator. got a factory safety of 6.43. Okay. Now, factory safety ratio of how much it can withstand to how much it is actually in it. So we've got a ratio of 6.43 here, which is quite high in this context. But again, I'm just trying to add a little bit of info here so we can see it from an engineer's perspective, where they commonly use a size of around about between 2 and 4 for factory safety. So what this is actually telling us, and it's not been asked to calculate this in the question itself, but what this is actually telling us is what we can afford to do is make that pin a little bit smaller. And if we can make the pin a little bit smaller, then we can make the component a bit smaller, which will make it cheaper to manufacture, and we can save our company some money. So that's sort of the scenario that we're trying to sort of work our way through here. But again, this is a bit of a recap for you. However, the main difference this time is double shear. Now, if you have a little look at in your workbook itself, there's some questions on calculating the area of pins, which is covered in a previous video, and also incorporate some of this information, so if you can mix and match them. But again, if you want to have a little go at some of these yourself, try writing your own questions, come up with some diameters, change the force values, get some answers, let me check them, and then we can move on to the next thing. Once again, thanks for listening, and any questions, give me a shout.